Hey, it's Mr. Shrum, and welcome back to the second part of Properties and Chemical Reactions, the physical science tutorial. Um, we left off on the changes in matter slide, and we can classify all the changes of matter around us into two main kinds. We have physical changes and chemical reactions. And if you remember, there were four indicators of a chemical reaction, and they are a change in color, one. Two is a change in temperature. Three is the release of some type of gas. And four, a precipitate forms. If you mix two liquids together and you see a solid developing, that's a sure sign of a chemical reaction. No chemical reaction takes place in this kind of change, a physical change. Physical change is just mixing, separating, and changing states. So the new substance there's no really new substance. It's the same substance, but it's changed forms. On the other hand, a chemical reaction results in new substances, new products. It's not always easy to determine what kind of change or what kind of change of matter is occurring. For example, when we heat water, bubbles form when the water reaches its boiling point. So we may think that water has decomposed and the bubbles contain oxygen and hydrogen gases. However, those bubbles are just water vapor. They are the same substance. The liquid water is the same as the gaseous water. The hydrogen oxygen did not separate. They're still together in H2O form. However, those bubbles, so they're not a new substance. Heating the water resulted only in a change of state. So you have to be a little careful here. A chemical reaction is more intense, something newer is created out of it. Which observations show that a change in state of matter has occurred? So overnight, dew forms on the grass, and vinegar has a strong smell. When dew forms, it's a change in a state of matter from water vapor to liquid. When vinegar evaporates, it also represents a change in state. The reason we can smell vinegar in a bottle is because it's evaporating. If two substances are components of a mixture, they retain their individual properties. They have not reacted with each other. We can separate the substances of a mixture using simple methods. For example, we can easily separate zinc and aluminum pieces from a mixture of metals with a pair of tweezers. This process of separating is a chemical change. In some cases, it can be difficult to tell whether two combined substances have mixed or reacted. For example, when we add sugar to water, sugar disappears. It might seem that there is a chemical reaction between the two, but it is just a mixture. Which actions show that mixing or separating occurred? Purifying water with a carbon filter, a soda fizzing when its cap is opened, a metal mixed with a very small amount of a non-metal to make a metallic alloy. So when we purify water, certain substances separate and they do not come through the filter. But no new substance is actually produced. You're just holding back certain substances so the water is free from impurities. It's still water. And likewise, when we open a can of soda or a soda bottle, it represents separation. The carbon dioxide that mixed into the soda escapes. And finally, a metal alloy is a mixture. Think of a metal mixture. An alloy has properties similar to each of its main components. In the real world, many phenomena include both physical changes and chemical reactions. It can be difficult to analyze these phenomena. Suppose we make a solution of sugar and water and heat it. Water evaporates, and this is a physical change. But over time, the sugar might begin to burn. That would be a chemical reaction. So something burning, that's a chemical reaction. Recipes for making caramel or caramel, depending on your pronunciation, depend on this burning process. You're intentionally burning. And sometimes we can't clearly define certain changes of matter as either a physical change or a chemical reaction. Likewise, not all chemical changes are the same. So we're going to look at some different kinds of chemical reactions. Types of chemical reactions. So we have those synthesis reactions where things are coming together to form a new substance. And then decomposition reactions, that's when things are separating to make new products. And two or more substances combine, synthesize. A chemical reaction in which one substance breaks down into two or more substances is decomposition. Combustion is what it sounds like. That's a chemical reaction that occurs when substances combine with oxygen to produce heat, light usually, and a new substance. A chemical reaction in which an atom from one substance replaces an atom in another substance. So it's the old switcheroo. Now, these synthesis reactions, two or more substances react to produce a new compound. Some synthesis reactions occur between two elements. One common reactive element is oxygen. Oxygen reacts with many elements to produce compounds. Rusting and tarnishing are two examples of synthesis reactions. In both cases, oxygen reacts with metal elements. In rusting, the metal is iron, and in tarnishing, we're dealing with silver, copper, and aluminum. A synthesis reaction can also occur between an element and a compound and between two compounds. Now here on the picture, a thin layer of corrosion called tarnish forms on aging utensils made from silver. So you can see a little bit there. So we have this video here in which we will observe a synthesis reaction, and then we're going to answer some questions below.
This is hot sodium.
I'll restart it.
This is hot sodium. Plunged into a jar of chlorine gas, it reacts to form sodium chloride, common salt.
Jazzy. Interesting. So let me hide that, get back to the questions. What are the reactants in the reaction? Remember, sodium and chloride. So if you don't know their properties, you can look it up if you need to. The reactants in this reaction are sodium and chlorine. Sodium is a soft, silvery white metal that is highly reactive. So a very highly reactive metal. Chlorine is a poisonous greenish yellow gas that has an odor and combines readily with other elements. So we have two pretty reactive reactants. Now, what's the end product? What do they become? So it becomes sodium chloride. Sodium plus chlorine becomes table salt, sodium chloride. The product consists of small white or transparent crystals that are odorless. What evidence supports the conclusion that a chemical reaction has occurred? Well, the product is not poisonous or odorous like chlorine, and is no longer a metal like sodium. It does not have the same properties as either reactant, and also the white dust in the video indicates that a reaction has taken place. And the chemical equation that describes this as sodium plus chlorine becomes sodium chloride. And then why is this synthesis? Why is this a synthesis reaction? To become one, as just one thing, sodium chloride. Now, decomposition reactions, the opposite of a synthesis reaction, is when a thing breaks down into two or more substances. A compound breaks down into elements or even simpler compounds sometimes. Now, this often requires external energy, such as heat, light, or electricity. That's because the products of a decomposition reaction have more energy than the reactant. So we need to add energy to the reactant. Electricity is a common form of energy used for decomposition. In labs, chemists use batteries to decompose compounds. And batteries help chemists determine whether a substance is a compound or an element. Electrolysis. I want to see the official pronunciation of this actually, because I always say electrolysis.
Electrolysis of water.
Electrolysis. It doesn't sound right, but okay. Electrolysis. Electrolysis of water is an example of a decomposition reaction. Electrolysis is the use of electricity to cause a chemical change. In this case, the electrolysis decomposes water into oxygen and hydrogen. Now, combustion reactions. This reaction occurs when a substance reacts with oxygen. And this produces a lot of energy in addition to chemical products. Many common substances that burn, like wood, paper, natural gas, coal, wax, gasoline, and oil, are made primarily of atoms of carbon and hydrogen. When we burn these substances, carbon and hydrogen react with oxygen to produce carbon dioxide and water. Usually, water is released in the form of water vapor. When the water vapor cools, it changes into liquid water. Combustion reactions need a small amount of external energy to start. So it's like the decomposition type of reaction. And that external energy is called ignition. One common example is the ignition of gas in cars. Each substance burns at or above a specific temperature, which is its ignition point. The amount of energy released in a combustion reaction is much greater than the energy needed to start it. The products of a combustion reaction have less energy than the reactants, which is why energy is released. The energy released in a combustion reaction can also speed up the reaction itself. And in some cases, this leads to an explosion because it's such a fast reaction. And combustion of fossil fuels such as coal and gas is the primary source of, well, it's our primary source for now, for our day-to-day lives. Replacement reactions. A replacement reaction has two reactants and two products. In this kind of reaction, atoms from one reactant replace the atoms in the other reactant. Cavendish's experiment, which we saw earlier, is an example of a replacement reaction. Hydrochloric acid plus zinc becomes zinc chloride plus hydrogen. And the word chemical equation shows that the zinc replaced the hydrogen in the hydrochloric acid. So you see how hydrochloric acid is in this present state over here. Then the zinc switches zinc chloride plus hydrogen and kicks out the hydrogen. So this is like a home wrecker. This is a replacement home wrecker type of deal. And the word chemical equation shows that the zinc replaced the hydrogen in the hydrochloric acid. The products, therefore, are hydrogen and zinc chloride. Another example of a replacement reaction is neutralization. And in a neutralization reaction, an acid and an alkali react to form water and a salt. So an acid plus alkali, the products you get are salt and water, salt and H2O. A person who has stomach acidity might take an antacid. And those antacids are alkalis, or is an alkali, and it reacts with excess stomach acid. The alkali mixes with the acid, and this reduces or neutralizes the acid in the stomach. So this is neutralization, if you need some stomach relief. Now we're going to match some of the descriptions. Here's the answers. Here are the answers. A combustion reaction involves burning. This reaction requires energy to start, but it releases more energy than is required to start it. Oxygen is always a reactant, and the products are usually carbon dioxide and water. A decomposition reaction occurs when a compound breaks down. This reaction has one reactant and two or more products. Energy, as from a battery, is usually needed to break the compound apart. So think of electrolysis. A synthesis reaction occurs when two substances combine to form one substance. An example of this kind of reaction is rusting, in which iron reacts with oxygen. A reaction that involves the replacement of atoms is a replacement. It makes sense, the naming convention there. And an atom from one reactant replaces an atom in the other reactant. Things are switching places. And this kind of reaction has two reactants and two products. An example of that is neutralization of an acid with an alkali. Cool. Now we're going to look at science in the news, smart materials. How is all this knowledge of chemical reactions helping us in the modern world? Well, engineers and scientists are always trying to create devices and materials that anticipate our needs. For instance, it seems that smartphones get smarter every 3 months. That's not necessarily true. Scientists have also developed smart materials that change their color or form in response to a stimulus. Another smart material is a shape memory material. This material can change its shape when heated, cooled, or exposed to light, but then returns to its original shape. Complete the activity on the next screen to learn more about smart material. So polymers, that's another word for plastic. You know, the invention of a new polymer can help with plastics, and this article links us to it. If my screen will load. Here we go. Now, a scratch on your brand new car can be expensive to fix. A teen has helped to make a new plastic that might do more than protect your bumper. It might make small scratches disappear. Interesting. And let's see. We'll just look at the main points. So the plastic is a smart material, one that can change when scientists apply stress, heat, or water. The material's flexibility comes from links between the repeating groups of atoms that make up the polymer. The healing powers, so to speak, come from the atoms of sulfur in the plastic. These sulfur atoms bond to each other to form a disulfide bond, holding the plastic in a particular shape, but under UV light, those sulfurs break apart. When the bonds break with the UV light, the material becomes kind of flowy. Emily explains, it can flow into cracks and imperfections in the material, healing scratches. Turn off the UV light and the sulfur bond together again. The sulfurs bond together again. Meanwhile, the scratches are gone. All those sulfur atoms made a nasty stink in the lab, and the reaction to make the material smells like rotten eggs. I kept apologizing to people in the lab for the smell, and she would like to be able to apply materials like hers to objects such as cars. If you had your car coated with a plastic, then it got scratched, you could first use the heat to activate the shape memory to bring the pieces closer together. She notes, then you could use the UV light to heal the leftover scratches. Okay, that's interesting, I guess. Yeah. And this is a good little power words or vocabulary words to take a look at. Cool. Now, read this article. What is unusual about the material? The material that she invented, Emily, can be easily repaired by shining UV light on it. Describe the two forms of the material that Emily synthesized. One form has a definite shape and the other form is soft and flows easily. What is a useful application for this new material? Cars, she thought, would be useful. Explain how the material changes form. Well, it has bonds between sulfur atoms that break when exposed to UV rays. The material becomes flowy and fills the cracks on the surface. The bonds reform when the ultraviolet rays are stopped. So that's an interesting case of putting this chemical reaction knowledge to use. And that brings us to the end of the lesson. So congrats on completing properties and chemical reactions. Go take the mastery test, and I will see you all later. And if you have any questions, be sure to ask me, email me, and I will help you as soon as possible. All right, see you guys later.